First of all, I'd like to thank the organisers, KTH, University of Stockholm and Nordita for their marvellous hospitality in providing us with a very stimulating meeting, or at least so far stimulating. What I wanted to do was to carry on a little bit from what Stephen Hawking said this morning as he was describing work that Andy Strominger, myself and Stephen were doing. And I thought the best thing to do right now was to describe a little bit about what the BMS group is and how it is related to extra black hole charges. So we're all used to the idea of the information paradox coming about because black holes only have a limited amount of hair given by the mass, the charge, the angular momentum of the black hole. But we need to first of all see why this is and see how you might go around trying to change this. So what one usually does when talking about black hole space-times is to think about stationary or static black holes and ask what the degrees of freedom are that are associated with them. And it's been well known since the proof of the uniqueness theorems back in the 1970s that they are categorized by M, J, and Q, the mass, the angular momentum, and the charge. Or if we want to be a little more precise about this, the L equals 0 and 1 degrees of freedom of the gravitational field, which give rise to the mass and the angular momentum. We could also add to that the linear momentum of a black hole if we wanted to. And for the electromagnetic field, we have, of course, the electric charge. We could have had a magnetic monopole charge if we wanted to. But in each of these cases, you could generalize it to other gauge fields where you could have electric charges or magnetic charges. For other fields, well, gauge fields. One reason why this is kind of limited is that because the space-times that you're looking at are static or stationary, these charges are things that you can measure at I0, at space-like infinity. So these are things which are sort of fossilized in space-time. They're there forever because we're dealing with stationary or static black holes. And so these are sort of an irreducible set of things that the black hole is described by. However, in any realistic situation, one is in a different position. One sits at Scri plus, and typically one will observe what's going on by looking at rays or matter coming out of the space-time. After all, Scri plus is where astronomers live, and you will be observing a black hole or perhaps a collapsing star, who knows what, by looking at what happens at Scri, not what happens at I0. And for that reason, you really want to be considering what the degrees of freedom are going to be at I0, at Scri plus, not at I0. At I0, the asymptotic symmetry group of the space-time will be, at least for asymptotically flat space-times, it will just be the Poincare group. But, as we've just discussed, you need to consider what happens at Scri plus because that is where the dynamics of the situation is going on. One isn't going to be able to understand the evolution of a system without asking what happens up here. So that's what the BMS group is going to describe, and that's what I want to concentrate on for the rest of this talk. So what exactly is the BMS group? The way to describe it is to think about the metric on the space-time near Scri plus. There's going to be a retarded time coordinate u, which measures how far up Scri you actually are. There will be a radial coordinate r, which tells you how far you might be from some central object. And there will be a set of coordinates which we can call z and z bar, which parameterize the two sphere that represent the section of the stride plus. So this is retarded time. This is some kind of radial coordinate. And these are coordinates on the celestial sphere, S2. Near infinity, you expect the space-time to be flat. And so you expect, if you try to ask yourself what is the metric, you'd start off by writing something like the s squared is equal to minus du squared minus 2 du dr plus r squared gamma z bar dz dz bar, which of course is just flat space written in ur z bar coordinates. This is the metric on the unit 2 sphere. But we know that there will be corrections to this metric. The first correction that you come across will simply be due to the mass. There will be a term that looks like 2 mb over r du squared. mb is usually referred to as the Bondi mass. And is related to the gravitational mass of the stuff inside. The second correction term tells you that this sphere here will in general be somewhat warped. There will be a term that looks like, again, a subleading term, r cz z dz squared plus its complex conjugate to make things real. So this is a sort of warp factor for the sphere, and it's damned by one parameter r. Then there'll be some extra stuff, plus dz, dzzz, du dz, plus dz bar c, z bar du dz bar. And then higher order stuff that at least for the time being we're not going to pay any attention to. These objects, C and MB, are related to physical things going on in stride. MB, as I said, is the Bondi mass, but the Bondi mass can evolve because this space-time is a dynamic object, and the evolution of the Bondi mass is given by some order between CMB by du is equal to 1 The idea is to figure out what objects, what ordinate transformation preserve the asymptotic form of the metric. So the metric at R equals R goes to infinity is preserved by, I'll leave out the Rhodes transformation because they're not really relevant to this. So super translation and a little bit more. And in terms of coordinates, this is just simply the shift of u, retarded time, by any function on the sphere x, z, z, r.
It's not showing up on the screen. If you look, you'll see what you're writing.
I know.
Going down.
Will you move the camera to the other blackboard, whiteboard? Please. The left one.
Yeah, that one.
Good. Yeah.
You also need to make changes in R and Z, and they will be given by R minus Z, Z, F, and then Z goes to Z plus 1 over R dz F. This capital D is covariance derivative with respect to the sphere vector channel. So this is the asymptotic symmetry group. You can immediately see this, that this group is an infinite dimensional radius group. Another way of looking at the same thing would be to ask yourself, what would be the infinitesimal, what would be the vector field that generates this transformation? And you call that vector field psi. And it could be something like F d by du. What should be Z? Z F d by dr minus 1 over R dz F d by dz plus 1 plus 1. So there's a nice vector field that is associated with this. And roughly speaking, any real function f z z r will generate the transformation, but it allows the translation. And that's why this thing generates a dimensional group. But that is abelian Boltzmann pattern. What we're doing is adding f here and add the factor. That gives you rise to the abelian. You can see that this object changes both the body mass and the warp factor, because if you compute the Lie derivative with respect to psi, the body mass, there'll be f from the body mass. So that's a physical change in space-time that leaves the asymptotic form invariant. Similarly, you can change the warp factor, the Lie derivative of czz, f times the new function minus 2 minus dz squared for f. So this tells you that if the gravitational radiation is going to be described, it will change to C, but it corresponds to a super translation. So that is part of the physical meaning of the BMS translation. a nice formula to construct. Let's suppose that we have some gravitational radiation going to the sky, as we have there, and that down here, there's an initial point, a final point, and the radiation is concentrated in that region. What would be the effect of that radiation? Well, the easiest way to work this out is to think about this function C, the Hall factor for vector. The simplest thing to do is to observe that it obeys the equation dz bar squared czz minus complex conjugate equals 0. That implies that the scalar potential for Z, or scalar potential for C, and czz could be equal to -2 dz squared acting on C, a scalar potential. And that if you perform the BMS transformation, it just simply shifts this potential by f. You could do a little bit more than that. You can, for example, suppose you have some gravitational radiation here, and ask yourself, what kind of BMS transformation do you actually find as a result of some gravitational radiation going through the sky? So you can write down a nice formula for that. Which I think most simply is written in the following way. Change in C from before any radiation happens to after when there's any radiation is given by the integral over here, e to z prime, factor of metric on here, over some 93 function if I'm not going to write that. And then, time, integral to u, or t u u, plus in formula. This will be the initial, the final. And t u u contains two pieces. Effectively, the bit of gravitational radiation. So it would be a quarter of n squared. And if you use whatever that is.
Yeah. No.
So what this shows you is that if you allow gravitational radiation to flow through the sky, then it affects just the BMS transformation. So spacetimes which are flat asymptotically are not necessarily all the same. They will differ by BMS transformation. One way in which you would observe this is by what's usually called gravitational memory, discovered by Rogitsky and Shaw in the context of gravitational wave astronomy. Suppose that you have the Earth here, and you had some satellites which were sitting around the Earth, perhaps equally spaced. I don't want to draw it much more. Suppose these satellites were somewhere in the sky, and they were equally spaced. You allow gravitational radiation from somewhere to flow through the field, something like that, for a short time. And ask yourself, what will happen to these satellites? Well, of course, after the Right. Forgive the experiment. Do you want to get rid of this one? So you can have BMS charges. How are these going to be defined? Well, the simplest way of doing this is to think back to, I guess originally, work of Piles, but subsequently many others. It started with him as he wanted to construct a covariant way of looking at Poisson brackets. So what he did for an arbitrary relativistic field theory was to give an algorithm for constructing a covariant form of the Poisson bracket, one that does not require you to pick a particular time coordinate. This was followed up for the case of general relativity by Ashtekar, Krunkovich, assuming that's how his name is actually pronounced, Witten, and subsequently many others, which one of the most important for us are Wald, Lee, and Zupas. So they had a covariant way of describing Poisson brackets. That means that they invented a symplectic form on the space of all metrics and first derivatives. The form of this function is quite complicated, so I won't write it down in detail, but just tell you what it is. So we'll call it omega, as most symplectic forms are called omega. It depends on some background metric, and it depends on two perturbations from that background, h and h prime. And it's equal to some integral over any space-like surface, d3x, square root of the induced metric on it, unit vector normal to it. Since this is a space-like surface, the unit vector normal to it will be t, some vector, and it consists of things that look like h grad h prime minus h prime grad h, with a whole collection of different index orderings, and then finally a vector that sits here. If h and h prime obey the linearized equations of motion, this object in here is divergence free. That enables you to define a charge. You can't easily fix the charge, but you can easily fix the variation of the charge. Suppose that G went to G plus H, and H prime was the gauge transformation associated with a vector field that generates a symmetry. Then you'll have an object which is essentially a conserved charge, and what omega of G, H, grad psi represents is the variation in the charge due to a perturbation H corresponding to the symmetry psi. So that tells you that for any supertranslation, you are able to define a conserved charge. So take your favorite psi, that means choose your favorite f, decide you're going to vary the metric by adding, say, for example, c to it, given by the formula we had over there a little bit earlier, and this gives rise to a charge which you can compute. So what you discover is that this space-time, rather than being static, even though the black hole itself might be fairly static, there will be a whole collection of BMS charges which characterize the space-time. Beyond the mj and q that we had earlier. This could be a black hole space-time. It couldn't really be a static black hole space-time. It would be a space-time that is evolving. But there would be a whole collection of charges which would change as functions of time. So what we have done, or as the black hole evolves, that is. So what we've done is to construct an infinite number of charges that relate to the black hole. Well, that's just the BMS charge at infinity. We heard this morning about the BMS charge associated with event horizons. Well, perhaps I shouldn't say event horizons. I think I really mean isolated horizons, because an event horizon requires a global construct, whereas it seems to me we should be thinking about local constructs here. A clue that such a thing is possible, at least this is how I thought of it. Stephen may well have his own way of thinking about it, but this is the way in which I thought about it when listening to Andy Strominger. If we go back to our picture of the Earth surrounded by collections of satellites, something like this, then of course I said that the satellites are going to be out at Scry, out near infinity. But in actual fact, it doesn't make the slightest bit of difference where they are. You're just looking at them from Earth. So you could really sort of let them go down any null ray you like towards the Earth, and the physics of what's going on wouldn't change. The calculational details would change because what we did for the BMS group relied on being able to expand things in powers of 1 over r nicely and have some kind of asymptotic region and a controllable power series expansion telling you what happens as you get towards Scry. But that doesn't change the physics of it. You could just simply bring these things in, and at some point, well, if it was the Earth, you'd stop when they crashed, but if it was a black hole, you'd have to stop when you got to the event horizon. So you need to ask, what kind of structure would you have to have on the event horizon? So I will talk about isolated horizons. So these are null surfaces with topology S2 cross R. They are going to be so what I mean by null is that any normal to it is going to be tangent to it. So the corresponding vectors would be L. And I would like the convergence of the null geodesics associated with L to be have zero convergence. So what that means in practice is that HAB, I guess I should call it del A LB, this thing has got to be equal to 0, where HAB is the metric on the S2. Under those circumstances, you can write down what you think the metric is going to be. In general terms, it will look something similar to the way in which things look at scry. One could say there's something times du squared. Then there will be something involving a du dr. And then there will be some stuff that tells you about what happens on the sphere and distortions of it. U, beta, and W and G will be functions of the coordinates, but they're such that on the horizon, U equals W equals 0. And you can ask yourself, what is the corresponding symmetry which preserves this form of the metric in the same way that the BMS group preserved the supertranslations preserved the asymptotic symmetry for an asymptotically flat space-time at infinity? The answer is the corresponding vector field is f d by du. Again, f will be some function of z of the xa's, metric on the sphere, minus, and now something a bit more complicated, the integral over r from horizon to wherever you want to be, wb db of f dr prime d by dr minus the integral from RH to R G BC dB of F dr prime dc. So those are the generators of BMS transformations on the horizon. Similarly, you can construct a collection of BMS charges on the horizon. So what this tells you is that rather than black holes being dead objects specified by a small number of quantum numbers, this tells you that there are in fact classically an infinite number of charges which are essentially conserved objects. And for that reason, it gives you a potential way out of the information paradox. That's essentially the observation that led to what Stephen was talking about this morning. So various questions, of course, emerged from all of this, some of which were hinted at earlier. The first is that this is an entirely classical calculation. It's not a quantum mechanical calculation, and to understand the entropy of black holes, coming from the Bekenstein-Hawking entropy formula, one really should be doing a quantum mechanical version of this calculation. A second problem is that the way this was expressed was just in terms of perturbation theory. What one should really be doing is calculating BMS charges at past infinity and asking how the whole system evolves as you move to the future, where there is both a black hole horizon and scry plus. A third question, which should have been asked this morning but didn't seem to have been, especially given that there was a lot of talk yesterday about it, is that black holes made of baryons and black holes made of antibaryons look the same. Whereas in this kind of picture where things rise from gauge charges, that could not possibly happen. The answer is perhaps controversial, but relates to what Gerard 't Hooft was saying this morning. It restricts the kind of models that will be compatible with this kind of picture. Baryon number is a global charge, and as such, it is different to a gauge charge. In string theory, there are no global charges. Baryon number will result from a collection of other things which are associated with gauge charges, having to do with how one generates the standard model from fundamental string theory. So in string theory, you would not face that problem. But if you just simply constructed a general arbitrary model, then you would. Another question that is important is this enough charge to resolve the information paradox, or perhaps too much? I can't really give the answer to those questions. However, for gauge fields, not just the gravitational field, there is an analog of the BMS group. So for example, for the Maxwell field, there is an analog of the BMS group at Scri, which would enable you to say something about the electromagnetic hair of the black hole, not just its gravitational hair. Lastly, and related to a point also made this morning by Paul, who asked about black holes in other space-time. Since this is the effects here are associated with horizons, not necessarily just what happens at Scri, there will be this whatever kind of horizon you have embedded in whatever kind of space-time there is. But at any form of infinity, there will be some analog of the BMS group, whether it's a time-like infinity or perhaps unpleasantly a space-like infinity, which you probably don't really want to contemplate. But also, there will be an analog of the BMS group at cosmological horizons, which we have not scratched the surface of yet. So, as you can see, this is a sort of brief sketch of what is going on, and plainly there is ample scope for rather more work and firming up this to make sure that it really does work properly. So, thank you for your attention.
Let the discussions begin. Questions?
I understand what you're talking about.
Yeah, you are inaudible. But, well, just talk to me.
No, the rest need to hear as well.
Is this one on?
Yes.
It is. Okay. If I understand what you've described, it's a way of classifying classical gravity wave perturbations of a black hole. And when you say there are an infinite number of charges, conserved charges, that's a way of classifying the infinite number of ways that you can gravitationally perturb a black hole.
Yes, exactly.
Which is all, as you point, is all classical. But it seems like there's still a big jump from that to seeing how these charges or perturbations leave an imprint on the outgoing Hawking radiation. Do you have any ideas about that?
None that I'm willing to discuss at the moment. So let me say a few words about that. Maybe this will be news to Stephen. At the end of September, I will be going and visiting Andy Strominger for a couple of weeks, and we will attempt to produce a draft. Andy Strominger will then come to Cambridge in late October, and we intend to finish the draft then. So, yes, that is one of the questions on our mind, but I would not at this point like to give you an answer to that question. Mike?
Is this not working?
No, that's not working. But that one might.
There's
switch it off.
control on the bottom.
On the bottom there's a button.
Press the button on the bottom. So press the button on the bottom.
No, that's working.
You said that mass, charge, and angular momentum were the only quantum numbers. But in the case of supersymmetric theories, the extremal black holes form supermultiplets. And the other members of the supermultiplet could carry spin or non-abelian quantum numbers even.
Yes, they could.
And it's the fermionic hair that supplies those. Does that enter into your considerations?
Well, it has not entered into our consideration. I class this question as being part of, is this enough hair? So certainly in supersymmetric theories, it's presumably the case there is some analog to the gravitino, although I have not made any attempt to investigate what that might be. For supersymmetric gauge theories, then of course, since we know that there is an analog for electromagnetism, then you'd have thought there should have been an analog for the fermionic superpartners of the photon if in a supersymmetric setting. So I would think that the answer to that is yes, there should be such things, but we have not considered them yet.
Maybe Jim can repeat the question he was asking this morning.
Could you comment on the quantum cloning issue? Because you're saying that you're getting the information essentially onto the horizon through these BMS translations. And on the other hand, the particle that is falling in still is not perturbed very much going through the horizon, so that it should have essentially all the entanglement still have all the entanglement at the outside that it would have had. So in some sense, there is cloning of information. On the other hand, I think we can argue that there's no one observer that could detect both copies of information, because the information that's coming out at late times in the Hawking radiation is spread over essentially the whole future history of the black hole, while there's no observer that can both measure that and, in principle, detect that and also detect something inside the black hole. So,
yes.
Do you have any comments on that? Or?
Well, I think that you have put your finger at the heart of black hole complementarity, which I will confess that I've always found rather puzzling. Perhaps I'm not unique in that respect. And I don't know if Stephen is going to agree with what I'm about to say. But I find myself in Gerard Assuft's camp on this subject, that it is presumably the case that the two different observers are telling you different faces of the same thing. How that could come about is absolutely unclear to me. The alternative is simply that the nature of reality is not as objective as you think. You may take your pick. Maybe Stephen would like to say something on the subject.
Okay, so if nobody has something to ask, then I'll ask something. I understand that this is a classical calculation, but I was wondering if you know the recent work by Dvali and Gomez, where they are suggesting that the black hole is a condensate of gravitons and it has quantum hair. So this is explicitly a quantum picture, but they are saying that in this way you can store the information and then leak it out. Do you know this work, and do you see any kind of relation to this?
I will confess that I have not read their paper. Do I see any? Well, by a quantum condensate, I'm a little bit confused about what this might mean. So you just simply mean like a Bose condensate of something?
Gravitons.
The surface of which is
very long wavelength
horizon.
gravitons.
Is that?
they're considering long wavelength gravitons that condense basically in their own potential.
So that would be like saying that the black hole was something like the liquid phase of gravitation.
Sorry, I didn't.
Would that be like, is this thing on? Yes. Would that be like saying that somehow the black hole was like the liquid phase of gravitation?
Yeah, I think so. I don't think they put it this way, but
But maybe. It's kind of strange that if you look at the first law of black hole mechanics, then, of course, this represents work due to spinning the black hole up or charging the black hole up. But if someone just said, well, I have a mechanical system that has a term that looks like dA times something, you would say, this term represents surface tension. Like in a bubble. And you would say, well, that's what happens, it's the work you've got to provide if you want to increase or decrease the size of that bubble. The problem with that is that this rule for describing the mass of the black hole is a precise rule, classically, and is really inconsistent with all of thermodynamics. There is no temperature involved in this, and there is no entropy. So, for that reason, I find it a little suspicious that one wants to interpret things in that way.
Just remark, I'll talk about that tomorrow.
Thank you.
Would these considerations mean that the radiation seen at infinity is different from a usual thermal source?
You mean, would they be precisely Planckian?
Not only Planckian, but the lack of all kinds of correlations and so on.
Well, I think what would actually happen is that at the beginning of the evaporation process, they would actually look fairly Planckian. But by the time you got to the end, there would be significant deviations from that, because that's where you would expect the correlations to lie.
So it's no longer a perfect thermal source.
It would not be perfectly thermal. There would be corrections, and in particular large corrections when the temperature became large.
Okay, that's interesting.
Carlo, you...
Just a thought. The imprint you're looking on the horizon is not just on the horizon, it's also outside the horizon.
Mm-hmm. Yes,
in fact, you can find it, the metric somehow in a region outside the horizon. But just for what you said, seems to me. You're looking at its value of the horizon, but there's a similar imprint at various radii.
But you have to have a surface on which there is a collection of symmetries which you can regard as sort of the boundary of the space-time you're interested in, if you want to define charges. Otherwise, yes. The point is, of course, that you need a surface, which would be a time-like or a null surface.
Yeah.
But if that doesn't have any isometries, or any approximate isometries, then you can't really define conserved charges in this way.
Yeah, that sounds...
But what you're saying is, I think, that if you were very careful and you calculated all the back reaction properly, then you should be able to account for processes like this simply by being very careful.
That's right.
True at the classical level, but I don't know about the quantum level. The quantum level is something that we have to investigate more thoroughly.
That's right. Your answer is the answer of a mathematician. If I want to define the proper charges in that case, to take into account of, let me use this language even if my right person here disagree, where the information is stored of the incoming, then I can use these charges. But physically, the metric outside, of course, if I'm a great mathematician and I can compute it, still has this information. So is there any sense, given that, is there any sense for which what you said implies that information is precisely on the horizon as opposed to just outside the horizon?
The answer to that is not clear. However, you could make it clear by doing calculations which are in progress, which involve doing expansions of what happens near the horizon when you drop things in.
Yes.
And asking what the charges are before and after you have done that. That's a calculation which is in progress. It could be that you discover that the charges are not zero, in which case you would say that it was actually on the horizon. Or it could be you discover all the charges were zero, in which case you have to say it was outside the horizon because you're dealing with conserved charges. So that's a matter that is on our mind, or at least it's on and in my mind. I'm not sure about Stephen.
Well, maybe I think I would like to understand a little bit better the nature of these charges. So let's talk purely at the classical level for a moment. We have a Schwarzschild black hole. We perturb it a little bit with some gravity waves. Now, normally, of course, as seen by a distant observer, the perturbation will decay away exponentially. And after a while, the black hole is looks almost exactly the same as it was before the gravity wave came in and perturbed it. But you're telling us that there is, in some sense, a conserved quantity.
There's still an imprint of that.
There's an imprint of that, so that this conserved charge says that in some sense, once you kick a black hole, it's never the same again. Is that a fair statement?
I think
okay, but then that says that this imprint must be very, very hard to detect, classically. I mean, it's because we're dealing with something that is decayed away exponentially in time.
Yeah, well, what you're asking is whether or not this is enough to solve the information problem.
Well,
really?
I'm still trying to understand the nature of these charges, even in a classical theory. I mean, I can see there's a formal construction of them, but I think it would be a little hard pressed to ask an astrophysicist how to construct something to measure these charges, especially for a perturbation that happened a very long time ago. Can you say anything about that?
On the subject of how you measure them for the black hole, I'm not sure of the answer because that's a bit hard. If you want to measure the charges at infinity, then experiments of the type of the satellite experiment observation that we were talking about should be sufficient, at least in principle, even if not in practice.
Well, I think what you're talking about there is the gravity wave comes by.
Yes, exactly.
There's some geodesic deviation which occurs, and as a result of that geodesic deviation, the orbits then are different from what they would have been.
That is correct.
And that remains the same. But in the case of a horizon, it's much harder to see what remains to be observed at a later time.
Well, I think Gerard was talking about how you get around that particular problem this morning. I don't think I can put it much better than he did.
Another way I see this is that you have to look at the states asymptotically. When Hawking radiation comes out of a black hole, it can come out in very many ways. So you make a detection of particles. You have detectors all around the planet Earth, or the black hole, much like you sketched that. And all these detectors detect particles yes or no. So some of them go off, some of them do not go off. So that gives you a tremendous amount of information about the final state. Now, whenever you tangle with the ever so little with the ingoing states in the black hole, the outgoing states will be different. So from that moment on, you're looking at a different state, which means that different detectors will go off at sufficiently late time. And
but this is not in classical GR that he's considering. This is in the full theory you're considering.
Hawking radiation, of course, is not classical GR. So Hawking radiation is a quantum effect. So, and it is in that radiation where you see all these differences take place.
The question was about classical GR charges, if I understood it correctly.
Yeah, I was just trying to understand that classically we expect perturbations to decay exponentially in time. And now, certainly, as a matter of principle, a decaying exponential is never strictly zero.
Right.
It gets awfully close. So this conserved charge seemed to be a very subtle quantity and very hard to measure, even in classical theory.
So if you have a sphere of satellites that stay just outside the horizon for a very long time, and they have clocks, and they, at some point, they're all synchronized by themselves. They wait long enough, and then the difference between the clocks read the charges of...
That's fine, except you've got to keep them there somehow.
Okay. Well, with bars.
You mean, can I calculate entropy? We have not done so yet. The problem is that you see an infinite number of charges here, whereas, and that comes from looking at the classical phase space of the system, whereas what you want to do to calculate entropy is look at the quantum mechanical version of the phase space. That requires you to modify the structure of the phase space, typically by deforming Poisson brackets into commutators, or something of that type. And in this particular case, I do not know how to do this. Various people have made various suggestions. One suggestion was that you just simply put in some kind of cutoff, but how you would arrange for that cutoff to give you precisely the right thing in a way that didn't depend on how you did it is beyond me. I think that what one should be doing is looking at the quantum version of the phase space and then seeing if you can reconstruct the entropy from that without doing anything strange. But as of this moment, I don't know how to do that. Although I thought you did, actually.
So do you consider in the scenario that the singularity is still there or that it is kind of resolved? So I'm a little worried that if you look at the quantum version, that the gravitons that you have escaping to infinity have an entangled partner that falls into the singularity and you get the same problem again.
I have no idea about the singularity. Of course, the singularity is an entirely classical construct. Whether or not it persists in the quantum nature of space-time is unclear to me. I think ultimately your question really is about black hole complementarity again, because you're asking about what happens to observers that fall into the black hole rather than observers that stay outside. I find it rather hard to give clear answers on that question.
So if another question, the two metric, if you foliate, the two metric is not...
The 3 metric on the horizon is null. The 2 metric is sections of that which exist on the sphere. Same is true on scry.
Sorry, I got...
The 3 metric is a null degenerate
right,
metric.
but if
sections of it at constant advanced or retarded time will be 2 spheres.
It's exactly a 2 sphere. You mean it's a geometrical 2 sphere, not a topological 2 sphere.
Yeah.
So the charges are not written in this 2 metric.
So in this particular case, you see this could be any metric on a 2 sphere. For the case of what happens at scry, then you can use the unit 2 sphere, and there wouldn't be a problem. But here you've got to be a bit more general because you don't really know what shape the horizon is. It could be squashed, for example, in case it wouldn't be the same thing as 2 sphere, it would be conformal to it.
I'm confused. Suppose I'm doing a Schwarzschild in which things have failed.
Yes.
Different charges mean that the geometry is not exactly a 2 sphere or not?
Different charges would mean that geometry is not exactly, or will be deformed away from whatever it was that you started with.
So this is exactly the picture that the entropy that Stephen was asking about counts the possible deformation of a 2 sphere.
Well, classically, there are an infinite number of those.
Right, classically, which of course are infinite.
Yes.
It's in the old way, I'm not doing this anymore, but in the old way of loop quantum gravity, the counting was the number of quantum states, the number of quantum geometries, which they are discrete because of Planck length, with a certain condition. Certain condition being that the total area is fixed. I wonder if there's any. Somehow, the old loop quantum gravity calculation were based on the idea that you can view the horizon as a shaking sphere. And classically, it just, rapidly goes to an exact geometrical sphere, but quantum mechanically, intuitively keeps shaking. So you have to count the number of possible.
So you're basically saying that you could excite the horizon by making it vibrate.
Yes.
And the entropy is due to the thermodynamic nature of those vibrations.
Yes, that was the old, yeah.
So you mean you would fix the temperature and then ask what is the entropy, given that the energy is whatever it is?
Yes, exactly.
Maybe.
No, I'm not asking about that. I'm asking if there's a similar story here, because if there's some relation, because in a sense you're viewing the information stored into those deformations of the geometrical deformation of the horizon.
Yes, we have had discussions about that, or at least Andy and I have, and I think that Stephen had a discussion along those lines when we were in Hereford in April, but that has not yet been sort of made precise. Kind of thing that you might try to do, but we haven't completed that yet.
Does it matter if you have an eternal black hole or a black hole that formed from a collapse?
Well, an eternal black hole will be static. It's been there forever and it's unchanging. So those seem to be the things that we're not really interested in. Here, one's really interested in the question of black hole formation and evaporation, or at least black hole evolution, just for a little bit of time, which is a more practical kind of calculation to do. So eternal black holes are a little bit different. We could have a discussion about zero temperature black holes and entropy counting due to things like how you construct things with those particular quantum numbers out of branes. That works fine, but it only really works for zero temperature black holes. Those are static, and the charges corresponding to the brane charges are always things which you could measure at I0. So in some sense, those aren't really what you're interested in.
And next question, can you also use that for this approach and super translations for de Sitter space?
Yes, because there is an analog of the BMS group on cosmological horizons.
So in that manner, you would be able to mine information for what's beyond the horizon?
Perhaps.
Wouldn't
what went through it would be a better way of putting it.
So we shouldn't expect a thermal spectrum for a de Sitter space?
Well, maybe for pure de Sitter space you would, but for de Sitter space that contains some stuff.
Pure de Sitter should have zero entropy. It's a
Well, it
pure
has no
state.
observers in it. So. But for de Sitter space which contains some matter of some kind, which is more or less de Sitter space, then presumably the answer is yes.
But if you change the temperature and the spectrum, would that imply a sort of decay of the cosmological constant?
I don't see how that would come about.
Okay.
Can you define these charges on any null surface, or does it have to be a horizon or scribe
I
plus?
think it has to be something which has some kind of symmetry group associated with it, so that you can define the set of vector fields which generate that symmetry, and the charges will be associated with those vector fields. So the answer is no, not any null surface. Inflation. Well, that relates to the question about de Sitter space again. What I can say is that if you have de Sitter space, Then on the cosmological horizon, then there is an analog of the BMS group. If you have a black hole in distance space, there is an analog of the BMS group on its horizon. I don't really know about anywhere else.
Okay. So that would also provide a distinction between a radiation from a black hole and radiation obtained from an accelerated observer, since the latter wouldn't have the symmetries.
Well, an accelerated observer has a horizon, the Rindler horizon, and if you are going to ask whether that has a symmetry group associated with it, the answer is going to be yes. And so there must be some similar thing that tells you about things that may have fallen through the Rindler horizon, say, for example, inertial objects compared to the accelerated one.
I thought you just told me I couldn't take an arbitrary null surface, but surely I can take a null surface and then find an observer who's asymptotic to that. So I don't understand the relation between your answer to my question and the answer to the last question.
Simply because there's something very special about the Rindler horizon.
Well, but I can take any null surface and find some observer who is asymptotic to that, and then that surface becomes a Rindler horizon. So a moment ago you said that you could not have conserved charges associated with any null surface. Now you seem to be saying that a Rindler horizon would have conserved charges. So I see there seems to be a contradiction. Or am I missing something?
I don't think for an arbitrary null surface that there's a collection of observers that would have that as a horizon.
Why not? Just take some time-like observer who is accelerating closer and closer to the speed of light, so that observer is asymptotically approaching that null surface. Then doesn't that surface become a Rindler horizon for that observer?
Yes, but you're asking the opposite question, aren't you? You're saying, given a null surface, can you always find a class of observers such that it's their horizon? I'm not sure that that's true.
It seems to me the answer is, should be yes. Fairly obvious that you can take some time-like observers, an observer whose world line asymptotes to a given null line. And then that makes that line a Rindler horizon for that observer.
You need a whole surface.
Well, I take a family of observers who do that. So I see a contradiction between your two answers, unless there's something left out here.
I reserve the right to think about that overnight.
Any more questions? We can thank Malcolm and start with Carlos.